And then this plate you put two rivets. 1, 2, 3. And then you apply load to this plate. And then the plate will fail along this line. Fail along this line. Okay. So this is, we call it net tension failure. So this is net tension failure. Because net, why I mean net is area. So if you look at the cross-sectional area here, you have plate. So this is cross-sectional. If we cut the rivets, we drill a hole. When we drill a hole for the rivets, we have one here, we have one here, and you have another one here. So your area left is only between the rivets. So where you drill the hole is no more area. Okay. So what is the shaded area? We call net area. Net area because it has minus rivets hole. That's why we call net tension. So because now this area is smaller now, okay, with no hole, this area. Now as you drill a hole, the area become less. So as we understand, force is stress time area. So as area become less, the force is less. The force here is the load capability. Okay, capability to carry the load. Okay. Capability to carry load. So now, if you have less area, you have less force. So mean less force to carry the load. So if you maintain the load higher, then you now cut the hole, area become less, the load carrying capability of the plate become less, then you start to see the crack. So that's why, and this crack we call it net tension failure. So how to calculate the net tension failure? So first you have to determine, first step, you have to determine the A net. Say the width is 30 mm. The width of the plate. So when you do analysis 30 mm, you must divide by 1000 because you want to convert everything to meter. If not, you got this one wrong. Minus point. Minus, you have 3 fastener. Say each fastener is 4 mm each. So 4 over 1000. And then you got meter. And then next, you multiply by the thickness. Say if the thickness is 1 mm. Okay, 1 mm, 1000 mm. Now you got area A net. So that's what net area on the plate. So what's the answer? Anyone? Let me calculate. Anyone with answers? $30,000 divided by 1,000 minus 3 times 4 over 1,000 times 1 over 1,000. It is 0 and 0, 0, 0, 0, 1, 8 meters square. Okay, next step is you calculate the load carrying capability. Are you guys listening or not?
Yes, yes, bro.
Yes, boss.
Everybody is quiet. Understand or not? Anyone with calculator, please help. Please participate. Load carrying capability. If the ultimate tensile strength. Today we're using aluminum alloy 2024 T3 is a 400 mega. So the load carrying capability will be P load which is stress 400 times 10 to the 6 because omega. Pascal is Newton meter square times the area 0 and 0.00018 meter square. So meter square cancel. So P L equal. When you do this, don't miss the unit. You miss the unit, I'll mark off. You mark off, I mark off mean that you don't get marks. Please keep the unit as well. E6 times 0.00018. So you got 7,200 Newton. So those are load carrying capability. So 7,200 Newton. So if you apply 800 Newton, 8,000 Newton, then you will have the problem of the net tension failure. So you must keep the load below 7,200 Newton for you not to fail in terms of net tension. Any question?
No, Prof.
Okay, good. Then we go to the next one. The next failure would be shear out. Okay, shear out is under failure. It's under important failure. If you are looking at, if you are familiar with why we need H distance on the structure, I believe you have done it before on the previous structure class. You need to keep appropriate H distance because you may have a problem of this shear. Okay. So shear out this area, the rivet will cut through the edge and you lost the rivet strength capability. So here is, they call it shear out failure. And how you want to calculate the shear out failure? Let me explode the view. Okay. Say you have here the rivets, we apply 400 Newton. And then we have H distance. So here is H distance. So say we conventionally put 2 times the diameter. And the thickness, say, is 1 mm. So how to calculate? You need to calculate area A, area B. So what are those areas? Those areas, okay, if you put it in 3-dimensional, okay. So this area, this is one area. So this is another area. Okay. This area will be shearing off. Okay, So area A will be area 1. H distance time thickness. Each distance say 2 dimension. If the rivet is 4 mm, 2 over 4000 time 1 over 1000. So area 1. So what's the value? 4 over 1000 time 2 time 1 over. So you got 0.000008 meters square. Or we can say 1, 2, 3, 4, 5, 6, 8, 8 times 10 to the minus 6 meters square. So area 1 equal to area 2. So total area will be A1 plus A2, which is so which is what? 0.00016 meters square. So that is the shear out area. For you to calculate the shear out load, P shear out, we use a shear ultimate time A shear out. Say shear ultimate around 200 megapascal, 10 to the 6 Newton meter square. You multiply by 0.0000016 meter square. You need to keep the unit to cancel out so you can get some value in Newton. Time. So you got 3200 Newton. So that is the strength for shear out. Okay, now you apply 400 Newton. So means that you are safe because you only apply 400 Newton. But how much, or are you sure it's safe? You have to calculate margin of safety, which you strength 3200, material strength, can carry 3,200 Newton, and then you apply load on the rivet 400 Newton. So the margin safety is 8. So you have 800% extra if you apply 400 Newton. Any question? Seem to be quiet. I think you girl can score. After this, I put the quiz, then everybody can score. And your assignment also, you have to do this. You have to do all this stress check. And that's, I just follow what the manual say, what the Airbus manual has guided us to do. Any questions?
Okay, sir.
Okay. I pause for 5 minutes and please have a look whether you have any queries, any concern. I think you are very good guys, very good groups. You understand all, then should be able to score very good in your final, your midterm, and doing superbly on your assignment. So bear in mind, all this will be in the final, in the midterm. Then I don't have much other thing. Basically, all the courses is focused on this because this is the thing that we need to give it to you. So hopefully you're doing well. And the question will be more complex, not as simple. Okay. But if you understand this concept, then it's no problem. Okay, next. If you have no problem, then okay, I will go next. So next, shear out. After shear out, we have cleavage. Okay, cleavage is not fail due to shear. Shear out is fail due to the shears. That's why we use for the analysis we use the ultimate shear strength. For cleavage, it seems to fail due to the tension. Then we use the ultimate tensile strength for the analysis. So cleavage is when you have a fastener. Say we have two fasteners. It tends to crack through here and also crack across. So this is cleavage. So how to calculate cleavage? It's almost the same as shear out. However, we just use we don't use shear here. We use ultimate. So for this edge distance, we how to calculate the cleavage. Just like everything else, we are calculating the load. Okay. The PS P load strength cleavage. We use ultimate tensile strength time edge distance. So load cleavage 2 ultimate tensile strength time pitch distance. So here is to calculate this failure and this one to calculate this failure. So if you use ultimate tensile strength is 405. So PS PLSC1 will be a 400 easier 10 to the 6 mega Pascal is Newton meter square. Then you time the h distance here 2 time diameter time thickness. Sorry, a big correction, a correction here. So here is ultimate shear strength ultimate shear strength. So you have 400 times 10 to the 6 Newton meter square times 2. Diameter is 4 times thickness is 1. So you get the cleavage strength. So 400 is 6 times 8 over 1000 times. Okay, you got 3200 Newton capability. So if you apply, if your reverse load is more than 3200, then potentially you have this cleavage failure. So you need to apply load for this design below 3200 Newton, or else you got this cleavage failure. So for another failure, you inter-revert failure. So you consider you can be cleavage to ultimate shear stress and time, pitch distance, time thickness. Actually, I'm putting the shear stress too high because 400 is not shear. 400 is tensile, but I keep it away just for convenience. So, say talking about 400 megapascal, 10 to the 6 Newton meter square. So pitch distance normally we multiply by 5 times diameter times thickness. So 400 10 to the 6 times 5 over 4 over 1000 times 1 over 1000. So you get around 436 times 20. 8000. So you got 8000 Newton. So if you apply higher than 8000 Newton, you will get the cleavage failure. So you have to work out on the reverts to the load to be below 8000 for you not to get into the cleavage failure. Question? No question, I move on. After
No question,
cleavage,
Prof.
okay, good. After cleavage, we have bearing failure. Bearing failure is a crash of the hole. If we have plate, okay, this plate will be crushing. So as you apply the load, the, the plate, the hole, the plate near the hole will be crushing. So those are, we call it bearing failure. How to calculate bearing failure is very simple. So this is cross section. So we just consider this hole here, the area here. Okay, the area acted by the rivets. So this area is diameter times thickness. So P bearing is uh, bearing stress time diameter time thickness. So as simple as that. So say bearing stress say 300 megapascal, 300 10 to the 6 mega Newton meter square times say diameter is 4 mm, thickness is 1 mm. And then this one you get some value of 306 times 4. 1,200. 1,200. Okay. So you fail at 1,200. You see the failure is the from the previous analysis. There is tendency of failure. The weakest one is on bearing. So bearing will be the weakest one. So you should not load the fastener to higher than 1,200 Newton for each fastener, or else you have failure in terms of bearing. No question? I move on. You guys very good. So another one is pull through failure. Pull through failure is when the rivets actually uh, rivets or fasteners used to handle shear load. So we have plate, we install another plate, and then we join the plate by rivets. So rivets are taking out shear. They don't take tension. However, in certain situation, you may have excessive bending. Maybe the rivet is under bending. Okay. It goes through bending. We pull here, we pull here. And then this is bending. Once you have something bending, if you bend something, if you refer back to what we have learned, this is a plate, this is a cylinder, and you bend them, so the top one will be under tension, this one under compression. Once you have tension, it try to pull away. Try to pull away, it will fail. It will fail around the underneath the head. So this one we call it cleavage. So in other words, if we have a plate and plate, you have the reverse head here, you have the shank here, you have this form heads here after you working bar. So the failure under the head here, that is we call it as pull through. Pull through. And you need to calculate that. How to calculate that? You have to calculate this area around the underneath the rivets head. So if we have a head here, okay, I explode the view. And this is the shank of the rivets. So this is the too big. So this is a form head after the backing bar. So we need to consider this area here. If we look at the area from the top, it is around. And then you have the rivets. So you need to consider shear off. This one is shearing off. So the area will be 2 pi r, that is perimeter. Okay, the circular here 2 pi r time the thickness. If you explode the area, you have like here 2 pi r thickness. You need to cut through the area for you to fail. So then for this situation, if we have 2 pi r is 2 because the diameter is 4 over 1000 time thickness. So those are the pull through area. Two time pi time 2 time 2 time pi time 2. So you got area of 1, 2, 3, 4, 5. 3, 4, 1.25 10 to the minus 6. Sorry, 10 to the minus 5 meter square. So what is the loading? What is the load? The load will be full ultimate shear stress because shearing off time the area. Say the ultimate shear stress is for 200 megapascal, 200 times to the 6 Newton meter square. You multiply by the 125 10 to the 5. 1.25 10 to the minus 5 meter square. You can cancel, you can cancel. 200 E6 times 1.5 E minus 1.2. So 2,500. So if the bending is so excessive on the fastener, if the bending which will give you axial load of 2,500 Newton, then you have failure in terms of flow through. But this is rarely occur because we don't design first the shear to carry bending. Sorry, revert to carry bending, revert to carry shear. Unless the design is very poor, you may get into the situation of where the revert experience bending and the bending translate into axial force which trying to fail by pulling through the skin. Any questions? No? No, I can continue.
Okay, sir.
Are you sure you're all okay? After this, I give you midterm on this. Okay. Now is shear. Have you learned this before? Or you just first time you see this? You're very quiet.
First time. First time, sir.
First time and you understand them all well. Good. So you have no problem later in your assignment, in your quizzes, in your midterm. I'm worried. You are so quiet. Can you follow or not? Are you following? You don't follow? Please be honest.
Following, sir.
Huh? Following.
Follow.
Sure. Faham tak? Follow boleh faham, boleh faham tak? Okey, tak apa. Kalau you diam, maksud you faham lah. So, I boleh taruh question cantik-cantik punya. Very good. Okay, then. 2 Fastener shear. Another problem with the fastener is failure in shear. And for you, for the manuals, all the information about fastener shears are given. However, we will try to calculate how shear will be calculated. So shear is basically we are trying to cut the fastener into two. So we have this fastener, okay, and then you have plate, one pulling this side, the other pulling the other side. So the potential failure is here. The fastener will cut into two, just like you use a scissor to cut them off. So again, it's just like any other. The load shear on fastener will be just ultimate shear stress time shear area. Okay. So then you got the fastener load. That's how they calculate the fastener strength, by multiplying the area as well and the ultimate shear strength. So this material here is reverse, and if we say P shear, say ultimate shear strength is 200 mega 10 to the 6 Pascal Newton meter square, and then you time the area is pi r square because the rivet is a circle, it's a cylinder. So 200 10 to the 6 Newton meter square times pi. If diameter the rivet is 4, the diameter 4, then the radius will be 2 over 1000 square. Sorry. N square. Then you'll be able to get the fastener strength. How much the fastener can take up. The load. How much load it can carry. 2 over 1000 time pi 215. 215. So this fastener will able to take 200 to 2500. Sorry, 2500. 2500. Sorry, this is wrong. 2500 Newton. Higher than this, the fastener will shear off. And then next, no problem here. And we'll go to bending. Fastener bending, which is something that not always occurred. However, we try to calculate how to calculate the fastener bending. So fastener bending, if we have plate, you pull the plate. If the plate is very thick, so the tendency of the fastener to bend. So you can take the analogy of a cylinder and then the cylinder under bending. So bending is a shear stress, either tension or compression. Moment I, I is modulus of I is the moment of inertia. Y is the natural axis, distance to natural axis. So this is cylinder. Distance to natural axis will be the radius. Moment is a force. So say if we had 100 Newton here, 100 Newton here. The fastener here, see the thickness is 10 mm. So it will be 5 mm. And the bending will be on the 5 mm. So the moment will be 100 Newton to the 5 mm, which is you calculate become Newton meter. Newton meter. So pi over 1000 times 100. So you got 0.5 Newton meter. And then for the here, pi to the 4, radius to the 4. So I will be to time time pi. Right? So it's very large number, 1.25, very small number, 10 to 11. So your axial stress could be 0.5 Newton meter time thickness 2 over 1000. I mean time radius 2 over 1000 divided by 1.25 10 to the minus 11. So 80,000 mega Newton. So mean that it able to bend this to fail, you need to be 80,000 meganewton. I mean, very huge. So it's not easy to bend this, and you need to have 80 thousand meganewton to make it bend, because the load is very small for this situation. So that's how to calculate the bending. So bending is just standard bending formula: moment, time, distance to the natural axis, divided by moment of inertia. You got the stress. That stress is axial stress, either compression or either tension, because when you bend something, you get tension or compression. Okay, that's for bending. Any question? No, then I will set a quiz for you on this. Then hopefully you can score. All right. So we stop here first. We continue with buckling and wrinkling. That is the last two that we have to do. Later on, we continue with the detailed loading analysis of the cutout.